Hello everyone, welcome back to another video. Today we'll be covering the third segment of functions, which will be on inverse functions. So what is an inverse function? Graphically, a function and its inverse fulfill the property that they are the reflection of each other on the line y equals to x. Here, I call fx e to the power of x, and for the inverse function, which is ln x, I will denote with f inverse x. As you can tell, if you tilt your device, the graphs are reflections of each other on this line y equals to x. To illustrate this point becomes this point on f inverse x, this point becomes this point on f inverse x, and so on and so forth. What are some other well-known inverse functions? The graph of y equals to sine x has its inverse, which is sine inverse x. Although we will need to restrict the domain, which we'll talk about how to do a bit later. The graph of x squared also has its inverse, square root of x. And again note, we will need to restrict the domain. So we know how to identify inverse functions graphically, but sometimes that might be a bit hard to see. Let's move on to some other properties of inverse functions. If you look at all the examples that I've given you, e to the power x and ln x, sine x and sine inverse x, x squared and square root x, you may see a pattern. They kind of cancel out each other. Sine of sine inverse x is just x. Square root x squared is also just x. And finally, ln ex will be equals to x. I've written this last example here. We can summarize this into a neat little formula. F inverse fx equals to x. And similarly, f inverse x equals to x. But do note the domain restrictions for these two to work, because these are composite functions. Now let's go back and refer to this graph. A point a comma b on fx, when transformed to f inverse x, becomes b comma a. This can be seen in my earlier illustration when I reflect all the points over from fx to f inverse x. Now because of this property, we can kind of derive that the domain of f is the same as the range of f inverse. If you're not convinced, let's look at this example up here. The domain of e to the power x is any real number x. As you can see, any real number x. And the range of the inverse function of ex, which is ln x, is any real number y. You can see that this decreases all the way to negative infinity, and this increases all the way to infinity. So you can see the domain of f is the same as the range of f inverse. Similarly, the range of f is the same as the domain of f inverse. Again, let's use this example up here. The range of e to the power x is y is more than 0 because of this horizontal asymptote over here. While the domain of ln x, which is the inverse function to e to the power x is more than 0 because of this vertical asymptote. Also, you can see that the horizontal asymptote at y equals to 0 becomes a vertical asymptote at x equals to 0 when we find the inverse function. Alright, let's move on to even more properties. How do we manipulate inverse functions in functional notation? Our first example here is fx equals to a, and this becomes x equals to f inverse a. How I like to think about this is I'm applying f inverse on both sides. So it becomes something like this. The left hand side becomes f inverse fx and the right hand side becomes f inverse a. And we already know that f inverse fx is just equals to x. Hence, x is just equals to f inverse a. A quicker way of thinking about this is flipping the function f to become f inverse on the other side. So flipping the f to f inverse, this becomes x equals to f inverse of a. This intuition also carries over to the next few properties. If I have the function gf of x equals to a, this is the same as saying x equals to gf holding inverse of a. Now remember that although gf is a composite function, it is ultimately still a function. So we can flip the whole gf over to the other side, and this just becomes x equals to gf holding inverse of a. This over here just denotes the inverse function of gf. Now this over here is not the same as saying g inverse f inverse. In fact, it's the complete opposite. Let's take a look at our last property. If gf of x equals to a, Flipping the g over to the other side, this becomes fx equals to g inverse a. And flipping the f to become f inverse on the other side, we'll get x equals to f inverse g inverse a. This also means that gf holding inverse is the same as f inverse g inverse. Before we move on to the questions, I've been kind of alluding to this earlier, that we need to restrict the domain when finding inverse functions. What's that about? This is because for a function to have an inverse, the function must be a one-to-one function. One-to-one means there's only one x value for every y value and one y value for every x value. That's a big mouthful and a lot to take in, but we can simplify this with this thing called the horizontal line test. If my function passes the horizontal line test, this means that my function is one-to-one. Basically what the horizontal line test is that I will draw horizontal lines for the range of my function. And as long as there's one horizontal line that intersects the function more than once, this means that I failed the horizontal line test and my function is not one-to-one, and hence does not have an inverse. Let me show you what I mean in practice. Let's look at this function y equals to x squared. If you see, I can draw a horizontal line that intersects the graph of y equals to x squared more than once. It intersects it here and here. This means that I failed the horizontal line test and my function is not one-to-one. Hence x squared does not have an inverse function. Hey, but didn't we say earlier that square root x is kind of like the inverse function to x squared, right? They kind of cancel each other. Well, that's where the domain restriction comes in. If we take the domain where x is more than or equals to 0, this red part over here, then this passes the horizontal line test, meaning that it is a one-to-one function and that it has an inverse. And this inverse is just y equals to square root of x. You can also confirm this graphically by seeing that they are the reflections of each other on the graph of y equals to x. Now I want to pose you an interesting question. What if I want to take the domain where x is less than or equals to 0? What is its inverse function? We know that this is a one-to-one function as it passes the horizontal line test, as there's no horizontal line that intersects the graph more than once. The inverse function is the graph that I'm going to draw over here. And this is actually y equals to negative square root of x. Again, you can see that these two graphs, the graph of y equals to x squared for x is less than or equals to 0, is the reflection of the graph of y equals to negative square root x on the line y equals to x. Okay, let's try our question. Given that fx equals to x squared plus 5x minus 2 and x is less than negative 2.5, find f inverse x stating the domain. Alright, so what we want to do is say that y equals to fx. And also, we know that this means that f inverse y equals to x. Okay, so let's start. We know that y equals to fx, so let's do y equals to x squared plus 5x plus 2. So what we want to do is isolate the x. And what can we do to isolate the x? We can do completing the square. So if we do completing the square, we'll get x plus 5 over 2 squared minus 33 over 4. And let's say we move this negative 33 over 4 to the other side and then square root the entire thing and move the 5 over 2 to the other side, we can isolate the x. Okay, so x plus 5 over 2 squared equals to y plus 33 over 4. What we want to do is square root this, right? So we get that x equals to negative 5 over 2 plus minus the square root of y plus 33 over 4. And remember your plus minus sign over here. When you move the 33 over 4 and do the square root, you need a plus minus, okay? That's where the plus minus comes from. But again, we can't have a plus minus. As you can see from over here, we have the positive and negative square root earlier, so we need to choose one of them. And how do we choose them? We actually want to look at the initial domain. So we see that x is less than or equals to negative 2.5. This over here is coincidentally negative 2.5. And if this is less than negative 2.5, this has to be negative, because if it's positive, we're adding a positive value, which will be more than negative 2.5, which is wrong. But if we are taking away a positive value minus a positive value, this is actually less than or equals to negative 2.5. So this fulfills the domain x is less than or equals to negative 2.5. So we reject the positive value of the square root because x is less than or equals to negative 2.5. Okay? So now that we're here, let's find out what f inverse is. So if x equals to f inverse y, we know that this over here is f inverse y. And what we can do to find f inverse x is just replace the y with an x. F inverse x, we're just replacing the y for x, minus square root of x plus 33 over 4. And it wants us to state the domain. The domain of f inverse is actually the range of f. Remember from earlier? So let's find out what the range of f is. We know that x is less than or equals to negative 2.5. And this is actually your minimum point. So your range of f will just be this entire thing from this point onwards upwards. So when x equals to negative 2.5, we get that y will be equals to negative 33 over 4. So y has to be more than or equals to negative 33 over 4. So this also means that your domain of f inverse is just x is more than or equals to negative 33 over 4. And remember, when we find the domain, we need to account for any restrictions, and we look at this restriction for the surd. We see that this fits actually perfectly into x is more than or equals to negative 33 over 4. So it also kind of checks out. We don't need to add an additional restriction to this domain. So we can accept this as our final answer. This, in fact, is just a question I pulled out from IB. The first step you always do is y equals to fx, means that f inverse y equals to x. Okay, so that's right. Y equals to e to the power x plus 1 over e to the power x. And actually, to isolate the x for this, we want to convert this into a quadratic in terms of e to the power x. So I'll have y e to the power x equals to e to the power 2x plus 1, which means that e to the power 2x minus y e to the power x plus 1 equals to 0. And let's see why we want to convert this into a quadratic equation. Because when we convert this into a quadratic equation, we can use the quadratic formula in terms of e to the power x. So you can kind of see this as a squared minus ya plus 1 equals to 0, and then find out what a is. So let's say I don't want to use all that substitution. I'll just go straight away. E to the power x equals to negative b. In this case, we are taking negative of negative y. So y plus minus the square root of b squared negative y squared minus 4ac. 4ac, which is 4 times 1 times 1, which is just 4 over 2a. In this case, a again is 1, so it's just over 2. And to isolate the x, I'll just take ln of y plus minus square root of y squared minus 4 over 2. Again, we look at this plus minus and we need to get rid of one of them. So let's look at the domain. For fx, x has to be more than or equals to 0. So if we want x to be a positive value, we probably want to take the positive side so that this entire thing will generally be positive. We'll be taking ln of a positive value. So let's do that. We'll reject the negative and we'll say that this is equals to ln y plus square root y squared minus 4 over 2. Okay, don't write negative like this in the exam. Write out the whole thing. So this also means that f inverse x, again, we're just replacing the y in here for x. It's just ln x plus square root of x squared minus 4 whole thing over 2. Okay, now we need to state the domain of f inverse. Again, the domain of f inverse is equals to the range of f. So let's find out what the range of f is. To find out the range of f, we want to look at the domain that they provided us and maybe any minimum or maximum points. But if we look at this, there's unlikely to be any minimum or maximum points because this will keep increasing and increasing. So we can just substitute in what x equals to 0 is, which we see e to the power 0 plus 1 over e to the power 0 is just equals to 2. And if we substitute in the other bound, where like x basically approaches infinity, we also get that this entire thing kind of like also approaches infinity. Okay, so we know that our range is y is more than or equals to 2. And knowing this, since the range of f equals the domain of f inverse, this is x is more than or equals to 2. And again, when we want to look at the domain, we need to find any additional restrictions. So if we look at this as an additional restriction, the surd, we actually find that this matches up pretty well. x is more than or equals to 2 actually fulfills the domain of this cert. So we don't have to put on any other restrictions to the domain. Hopefully this gave you a little bit more insight into how inverse functions work. Here's the summary sheet for inverse functions. And here's the summary sheet of all of functions.